When you look up at the night sky far from city lights, you will see thousands of tiny pinpricks of light twinkling in the vast backdrop of space. Each of these tiny points, as we see them from Earth, is in fact its own massive ball of hot plasma with a nuclear furnace deep within, which we call stars. Many of these stars have been shining uninterrupted for billions of years, and they will likely shine for billions more. But all of these stars don't just appear out of the vacuum. How exactly did these cosmic nuclear reactors come into existence? Now, before we get into the origin story of a star, I'd appreciate you like the video, subscribe to the channel, and hit the notification bell to stay tuned for future content. Okay, so before we can understand how these stars came to be, we need to understand a few things about the universe as a whole. A few minutes after the universe underwent its Big Bang, a topic which is fascinating enough to deserve its own video in the future, it went through a period where it was cool enough to produce atomic nuclei, but still hot enough for the pressure to overcome the forces keeping them apart, which allowed them to fuse into slightly heavier elements, a process known as nuclear fusion. This period only lasted a few minutes, but this was long enough to fundamentally shape what the universe is made up of today. Approximately 75% hydrogen, 25% helium, and trace amounts of elements such as lithium and beryllium, which are the following elements on the periodic table after helium. This composition has mostly survived to the present day, as the universe's expansion and cooling distributed these atoms across the universe. However, they are not distributed in equal quantities by any means. In many regions of space, hydrogen and helium clump together in gigantic clouds, known as nebulas, with densities just a few times higher than the density of the overall interstellar medium. On their own, these nebulas don't do a whole lot other than just drift through space without a care in the universe. But what happens if we introduce a disturbance, like a nearby star exploding at the end of their life or a black hole passing close by? Well, this is when the ingredients for star formation start coming together. So, how exactly does this start forming a star? Well, what these outside influences can do is cause certain regions of the nebula to get dense enough to exert their own gravitational influence. With the power of gravity, these regions will slowly contract, at the same time becoming strong enough to potentially pull additional gas from the nebula into it. As it contracts, it slowly heats up thanks to the matter within the region starting to get squeezed together. Keep in mind that this process takes quite a long time, on the order of tens of thousands of years, so you don't exactly have stars forming overnight. However, given that stars themselves go on to live for billions of years, this is basically nothing on astronomical timescales. After enough time has passed, the region of space becomes small enough and dense enough to rotate. This causes tons of excess material to be flown from the center of the so-called protostar, and this material ends up in a disk around it. If parts of the disk are closer to the protostar, it will fall back into it and cause it to grow. This process is known as accretion, and it's a very similar mechanism to how black holes gain mass. After a while, the protostar finally becomes small enough and dense enough for its core to initiate nuclear fusion, the same process that occurred in the universe's early moments. Since a nebula is, again, made almost entirely of hydrogen, the fusion that takes place turns that into helium while releasing energy in the process. This energy causes the star to actually shine for the first time, and can thus be seen from outside the nebula under the right conditions. Meanwhile, the disk around the star stops falling into it, and instead just orbits around the star. Over millions of years, the material in the disk can coalesce into planets and moons, either small rocky planets like Earth or large gas giants like Jupiter and Saturn that were able to grow big enough to pull some of the nebulous gas themselves. Over millions of years, the system will slowly stabilize and eventually settle into a rhythm that will be maintained for billions of years, barring a major disruption such as another star getting a little too close. Okay, so now that we know how stars form to begin with, there's one more thing to ask. What in this process determines its physical attributes? We're talking about the color, size, temperature, and overall lifespan of the star. Well, as it turns out, all of these seemingly unrelated characteristics can actually be explained by the same thing: how massive the star is to begin with. As you can probably expect, not all stars during the star formation process are created equal. Some stars are able to get more gas to fall onto them during the accretion process and grow larger, while other stars barely even get enough gas to initiate nuclear fusion in the first place. In addition to determining the raw size of the star, mass also determines how quickly nuclear fusion takes place in the star's center, which in turn influences the temperature and longevity of the star. Lower mass stars burn their hydrogen into helium extremely slowly, So they end up at a cool 5,000 degrees Fahrenheit or 3,000 degrees Celsius at the surface. Interestingly enough, unlike on Earth where red objects are considered hot and blue objects are considered cold, the inverse is true for cosmic objects due to the nature of radiation in general. Lower energy radiation has a longer wavelength and thus appears redder to us, while higher energy radiation has a shorter wavelength and appears bluer. As a result, these low mass stars are generally orange and red. In addition, despite having so little material to work with, these stars fuse hydrogen so incredibly slowly and have such efficient convection that they are expected to last for trillions of years before fading away. More massive stars, as you can probably expect, are just about the complete opposite. They fuse hydrogen extremely quickly in their cores, which releases a lot more energy and makes them a lot hotter, brighter, and bluer. This also causes them to use up the available hydrogen remarkably fast despite how much matter they have to begin with, oftentimes on the order of just a couple million years for the most massive stars. Then, instead of quietly fading away, they go through a roller coaster of phases, all dependent on what's happening deep within their cores, before finally violently exploding in a supernova and leaving behind a neutron star or black hole. As you can probably expect, our sun falls pretty much in the middle, with the amount of mass that it has being enough to sustain its yellow hue for about 10 billion years, a time span that we are just under halfway through. It is predicted that in about 5 billion years, it will slowly expand into a so-called red giant that might stretch all the way out to where Earth's orbit is now before quietly expelling its outer layers in a planetary nebula, so named because astronomers in the 1800s mistook them for actual planets. And here's where things get really interesting. The material ejected at the end of a star's life, whether it be a peaceful planetary nebula or a violent supernova, is still almost entirely made up of hydrogen and helium. As a result, once it is returned to the interstellar medium, it is possible for gas from several stars to come together, form a new nebula, and then another outside force causes this nebula to once again collapse and form a new star. Thus, the cycle continues, with stars constantly dying and being reborn as new stars, creating new planets, and potentially even creating new alien life. However, this cycle won't last forever, as there is always a little bit of material locked up in the degenerate cores of dead stars. As a result, over long periods of time, the universe's supply of gas and dust will slowly dwindle until at long last it is impossible for any new stars to form. And once that happens, the universe will grow cold and dark, hostile to any new life and even light, all becoming scarcer and scarcer until one day it just ceases to exist. But that time is trillions of years off, and for now, we can be grateful that we can look up at the night sky and marvel at the thousands of twinkling little points that dot it, knowing that they will shine long after we're all gone. And with that existential moment, that's all I have to say about stars. As always, I'd appreciate if you like the video, subscribe to the channel, and hit the notification bell to stay tuned for future content. Thanks, and have a great day.